This is the three-dimensional shape of a sound wave. Specifically, it's the collision of two 40 kHz ultrasonic blasts suspended in mid-air. In the last video we managed to film this interference pattern using a homemade Schlieren rig. It looked amazing, but as an engineer it really bugged me. We live in a 3D world, but my camera only captures a 2D shadow. We were looking at a flat slice of a volumetric object. I couldn't fix this with a better camera, so I had to fix it with matte. So today I'm going to take this flat video, feed it into some custom Python software, and reconstruct the invisible landscape of a pressure wave in 3D. To get the data I need to take a photo of the sound wave, then move the wave forward by a fraction of a millimeter and then take another photo. But sound travels at 340 meters per second. To freeze it, the camera, the sound and the flash need to be synchronized to within a few microseconds. And this is where normal computers struggle. A normal CPU is like a person reading a book. If you ask it to clap your hands exactly every second, it'll say, "Hang on a minute, let me finish this sentence and I'll deal with you next." This delay is called jitter. Now we solved the basic shaking in the last video just to get a live view, but for 3D reconstruction I need to stack multiple images. Even a few microseconds of jitter here doesn't just shake the image, it destroys my 3D view. To fix it I had to bypass the CPU and use DMA, or direct memory access. The CPU is like a person reading a book. It gets distracted by every sentence. But DMA is like a drummer. He doesn't care about the book, he just hits the beat on the sheet music perfectly every time. So rock solid, now we can get the data. I wrote a Python script to automate the capture. It moves the camera trigger by a few microseconds relative to the sound wave, takes a photo and then repeats, reconstructing the sound wave by adding all the images together. But we have a new problem. The images are noisy. The signal, the sound wave, is very faint. The noise, sensor grain and air currents are random. To clean this up we use two tricks. First is background subtraction. We take a photo with the sound off to see all the noise and the air currents and then subtract that from the sound on photo. Second, we use a trick from astrophotography called image stacking. If you take a bunch of photos of the exact same moment and average them together, the random noise cancels itself out to zero. But the sound wave, it remains. And remember, while we're looking at this image, we're also listening to it. And this is the sound of air being compressed, slowed down so you can hear it. Now that we've a nice clean 2D map, it's time to enter the third dimension. My first intuition was simple. Sound expands in a sphere, right? So I just take a 2D slice and revolve it around the center axis. A bit like a potter spinning clay. But I tried that and it looked, well, like a lumpy clay pot. It was technically 3D, but it was strange looking. This method only showed the outer shell and I ignored all the density changes inside the wave. So I realized I didn't want a solid revolution, I wanted a topographical map. So I rewrote the code to use displacement mapping. Now it scans every pixel and if a pixel is black, the map stays flat, but if a pixel is bright, the code pushes that point upwards vertically. It works exactly like one of those pin art toys, but instead of pins we're using light intensity. Now one final issue is that the background air in my shed isn't perfectly still. This creates low frequency rolling hills in the 3D mesh. So I applied a high pass filter. Now this chops off the slow moving background air and leaves only the fast moving high frequency sound. Now the geometry is finally there, but it was just grey. Now it's hard for the human eye to see the depth. So the final step was to apply a false colour map. I mapped the high peaks, that's the high pressure, to hot red and the low valleys became cold blue. When I ran the code, this happened. This is the landscape of a sound wave. You can literally see the texture of the sound. And when we turn on the second speaker, you can see the interference. You see the waves crashing into each other, forming new red peaks where they combine and faint blue planes where they cancel out. It looks a bit like a mountain range, but it's actually a freeze frame of two sound waves crashing into each other. Now this is all incredibly cool, but I have to be honest with you, it's still a bit of a cheat. This is a relief map based on a 2D photo. It's essentially a fancy height map. To see inside the wave like a real medical CT scanner, we need to do optical tomography, and that involves rotating the entire experiment while filming it. But that's exactly what we're going to be doing in the next video. All the code used to generate my images is contained in the GitHub down below. And thanks for watching. Now go and generate some cool 3D images.